Okay, we're going to start our nuclear physics unit. Um, the nucleus was discovered by Ernest Rutherford in the famous gold foil experiment, which you should remember from chemistry. Okay, his experiment consisted of this. He shot, so we're going to say Rutherford shot alpha particles at gold foil. And what he found is that the great majority of them, greater than 99.99%, went straight through. And from that, he determined that the atom is mostly empty space. But a tiny fraction would be less than 0.01% bounce back so they had to have hit something hard or dense. So he determined there was a tiny, dense nucleus down in the center of the atom. Now the composition of it, the nucleus is made up of protons and neutrons. There's some data here that you might want to use at some point. We know that the particles in the atom, in the nucleus, we have the proton and the neutron. Their masses are very, very close to each other. We found that out in our static electricity unit. The neutron is actually slightly heavier than the proton. And then outside the nucleus are the electrons, and their mass is much, much less. Well, we're going to write the symbol for a nucleus. We're going to tell the atomic number, which is number of protons, and the mass number, which is number of protons plus the number of neutrons. You should remember this from chemistry. So if I was going to write the symbol for carbon-14, when I tell you carbon-14, I'm telling you carbon with a mass number of 14. I don't have to tell you the atomic number because carbon always has the same atomic number, which we can look up on a periodic table. And there's one of those in your planner. And if we look up the number for carbon, its number is 6. So it has 6 protons. Carbon's always going to have 6 protons. This particular brand of carbon has a mass number of 14. That can change. You can have different isotopes have different mass numbers. Most carbon is carbon-12. This carbon is carbon-14. And so this carbon-14, I now know that it has 6 protons because its atomic number is 6. And it's going to have 8 neutrons because the mass number, 14, is the number of neutrons plus the number of protons. So if I subtract 14 minus 6, I get 8. Now, some nuclei naturally decay on their own. If you just wait long enough, they'll decay into something else. And there's 3 types of natural decay that we're going to talk about. First is alpha decay. And in alpha decay, a nucleus emits an alpha particle. I'm using the symbol for alpha. As the Greek letter alpha looks like this. And they later determined that an alpha particle has an atomic number of 2. It has 2 protons and a mass number of 4. And If you look up the thing that has an atomic number of 2, that's helium. So the symbol for an alpha particle is 24He. And that's something we're going to have to memorize. You need to know that to be able to answer alpha particle decay questions. So here's an example. We have uranium-238. It's going to undergo alpha decay. And I mentioned that it's going to produce a thorium nucleus here. I wouldn't have to give you that, and I'll show you why. So to do this problem, I'm going to start out with uranium-238. And then I have to look up the number for uranium. And if you look on a periodic table, it's 92. It's going to undergo alpha decay. So it releases a helium nucleus, an alpha particle. And then we have to figure out what is left behind. So this arrow here is like my equal sign. I have 92 protons, or a charge of 92. Charge has to be conserved, so I have to have 92 on the other side. I already have 2 here for the alpha particles, so this is going to be 90. And then the mass numbers also have to balance because mass is conserved. So 4 plus something equals 238. This must be 234. And then if I look up thorium, if I look up number 90 on a periodic table, I find that it's thorium. That's why I didn't have to tell you it was thorium. Because once you get this number down here, you're going to know what it is by looking it up on a periodic table. For beta decay, it emits a beta particle. They didn't know what it was when they first started talking about beta decay, but now we know that a beta particle is just an electron. Now an electron doesn't have any protons in it, but it does have a charge of -1. So we put -1 down here. And if you remember, the electron's mass is much, much, much less than a proton, so it's essentially 0. So we're going to put 0 up there. And again, if we have to memorize that that's what a beta particle is. And then the problem becomes pretty easy. Carbon-14 is going to undergo beta decay, producing a nitrogen nucleus. So we're going to start out with carbon-14. We look up its atomic number, and carbon is 6. It's going to decay by emitting a beta particle, which is an electron, -1 and 0. And we have to figure out what's going to get left over. So on the left side of my arrow, I have 6. I have to have a total of 6. On the right side, I have -1, so I have to have 7. And then on top, 14, here I have 0, so I have to have 14. So the carbon nucleus emits an electron, producing a nitrogen nucleus. This one's actually kind of interesting because we gained a proton and ended up losing a neutron, because this would have had 8 neutrons over here. This only has 7. So what actually happened is a neutron turned into a proton by releasing an electron in this reaction. The third type of natural decay is gamma decay, and it simply releases energy. So the nucleus releases energy. So energy doesn't have mass or charge, so the symbol for gamma decay is just the Greek letter gamma, and it has 0 charge and 0 mass. So these problems are going to be really easy. All right, I have radium-226 decaying, so it's Ra-226. It's decaying, and if we look up radium, it's 88. It's going to release a gamma decay particle, which has no charge and no mass. So the nucleus doesn't change. So these, with gamma decay, it's always going to be easy because our product is exactly the same as our reactant.